This is a picture of Blackbird, a wind-powered car that was built around 2010. Its performance is counterintuitive. This video deals with one of the riddles raised by Blackbird's performance, the riddle of the weak wind. Compare the small cross-section of Blackbird's propeller with that of sails of sailboats of similar size. How could such a slim propeller and a weak wind move such a heavy resting car, both upwind and downwind? We know that winds can move heavy things, as grinding stones in windmills and electric generators in wind turbines. But unlike wind-powered cars, those are parts of stationary objects. In the following, we'll talk about the basic science behind Blackbird's design that addresses that riddle. The forces that act on Blackbird act in 3 dimensions. In order to simplify our analysis, let us deal first with a simplified model, inspired by paddle wheels of watermills. That will enable us to focus on simple forces that act in 1 or 2 dimensions. Later, we will move to the more complex forces that act in 3 dimensions. Let us look first at a hypothetical car. A typical car has a propulsion wheel, or wheels, connected to the chassis. When an active propulsion force is applied to the propulsion wheel, the car would move in the direction of the active force. Consider now a hypothetical powertrain that would turn the wheels of the car. A wind paddle wheel and a smaller gear wheel are attached to each other. They spin together on a common axis. A propulsion wheel that spins on its own axis is touching the gear wheel. The combination of the paddle wheel and gear wheel acts as a lever. The input force of that lever is the weak wind force. The output force of that lever is the active propulsion force. Theoretically, that generated propulsion force could be as large as needed. It only depends on the ratio of the radii of the paddle wheel and the gear wheel. Next, we install the powertrain in our hypothetical car. It will move the resting car upwind if the propulsion force will be greater than the opposing resisting force, the purple arrow. That force is the sum of all the internal friction and viscosity forces that act on moving parts inside the system. It includes also the resistance of the air forces that act on the car's skin. Because of the lever effect, the requirement that the propulsion force is stronger than the opposing force could be satisfied, in principle, by an appropriate gear wheel. However, the car would not move if it were not for another force. The wind may spin the paddle wheel, which would spin the propulsion wheel. But if it were not for the friction force between the propulsion wheel and the road, all those wheels would be spinning, and that would be it. The propulsion wheel would be skidding on the road. Without sufficient friction force between the propulsion wheel and the road, the car would not move. Due to that friction force, the wheels are rolling and not skidding. In ideal rolling, no energy is dissipated by the friction force between the wheels and the ground. In reality, some energy is dissipated. This energy goes into deforming the ground and heating the ground and the wheels. However, in most cases and in the case of Blackbird, this energy is negligible. For the car to start moving downwind, a reverse direction wheel could be engaged in the gear of the hypothetical car, green wheel. Everything else would be the same as in a car that start moving upwind. Conclusion: the model presented here illustrates how a wind paddle wheel could move a resting car both downwind and upwind. It could be done, in principle, with gears whose lever ratios are large enough to overcome the internal friction forces of the car. However, a friction force between the propulsion wheels and the road is necessary for the car to start moving. In practice, there are more efficient ways to convert wind force to mechanical force. But wind forces have many riddles. We'll discuss them in the next presentation. The playlist Understanding Blackbird has more videos about this topic. If you like this presentation, please give us a like. If you would like to be notified about other posts of similar nature, please subscribe. Thank you.